afternoon. My name is Brian. As Aaron mentioned, I'm going to be adapting graphene liquid cells to image biomolecules in transmission electron microscopy. So first I'd like to begin with an overview of what TEM exactly is. So it's essentially a microscope that sends electrons through a sample in order to view it. Now you might be wondering right now why you want to use light. Well, the main reason is because light has wavelengths at roughly several hundred nanometers. So if you get these very small molecules that are less than several hundred nanometers, you wouldn't be able to view it in the first place. So this is what the transmission electron microscopy solves by sending electrons through, which have much smaller wavelengths. And just as an example, the TEM in our Zettel research group can get up to 2 angstrom resolution. And in addition, the NCEM electron microscope can actually get atomic resolution. So it can image atoms, just individual atoms. So the TEM is a very powerful tool, but there are challenges associated with it. So for starters, electrons don't like air. Air just scatters it everywhere. So in the electron microscope, you actually have to create a complete vacuum, or a very ultra-high vacuum. Now this causes biological preparation. It has to be very special. So you have to do things like drying your sample, freezing it, and treating it with harsh chemicals. So these can all create morphological changes in your biomolecule. And at the same time, you're not able to image the biomolecule in its native state. So there has been research done, and they've developed silicon wet cells where basically they have this silicon chamber where they can have liquid inside, and they'll be able to image biomolecules. So that's good. But the thing is that they're 50 nanometers. The windows are 50 nanometers, so it actually creates interference, and you get resolution problems. So this is where our research comes into play. So we are trying to adapt graphene instead of using the silicon to create these liquid cells. And the main reason we want to use graphene is because it's a hexagonal monolayer of carbon. So since it's just one layer of carbon, it can be very thin. It's angstroms thin. So an analogy would be, if you were to use the silicon system, you'd be looking at something through like 50 layers of window panes. While with the graphene, you'd just be looking at something through one pane of glass. So you get less interference and you get better resolution. And here's an artistic rendition of what the concept would look like in practice. So to give you a better idea of what graphene looks like, here's a TEM image of it. And I'd like you to notice that they're hexagonal. So there's these dots. Those are the carbon atoms, and they're in a hexagonal arrangement. So you might be wondering how we make the graphene. So the first step would be chemical vapor deposition. And an analogy for it is basically it's a sealed furnace with a reaction chamber inside, and you can use it to grow nanoparticles, or you can use it to grow nanolayers. And in our case, we used it to grow graphene, but it can also be used to grow things like boron nitride as well. So it basically works by having your gaseous reagents, hydrogen, ethylene, and methane, and they're pumped into this quartz tube. And there are heating coils that can heat it up to 1,100 degrees centigrade, so you don't want to touch it with your hands. And so what happens is that methane and ethylene are hydrocarbons, so they have carbon. And when you heat it up to 1,100 degrees centigrade, the carbons will dissociate and you'll get carbon. Now you'll have a copper catalyst inside, and the carbons will attach to it. And then when you cool it down afterwards, you get a graphene monolayer. So you might be wondering why we use copper. Well, it has to do with the solubility of carbon. Now, let's picture that this is a film of nickel. Carbon is very soluble in nickel. So these are carbon, and you could just imagine a metal solution where the carbon's actually getting inside. And when you cool it, it has to come out of solution. So you'd end up getting lots and lots of layers of carbon, which is what we don't want. So instead, we use copper, which is something that carbon isn't very soluble in. And what ends up happening is it gets mediated now by surface area. So you get a nice monolayer of carbon instead, which is graphene. So here are the growth conditions we had. For the very first stage, we would heat up or ramp up the entire oven, and this is under 10 sccm of hydrogen gas. And then the next stage would be a graphene growth phase when we introduce the hydrocarbons. And in this trial, we also had a second growth phase where we ramped up the hydrocarbon. And then finally, after the growth is finished, you cool it down so you can use your sample. And here's an image of the catalyst, the copper substrate, after we grew the graphene on it. So, now that we have the copper with the graphene on it, we want to characterize it in scanning electron microscopy. So, scanning electron microscopy is a method where there's a sort of like needle sort of thing which electrons will flow through, and you end up getting a topographical map of whatever substance you have. So we want to use this to confirm that we have graphene on the copper. So this is just an image earlier I showed you. This is just to remind you what graphene looks like. So we're ideally looking for something that's hexagonal. So in our SEM, we found this. Now this step-looking stuff is the copper, but we have this hexagonal region that's lighter. Now we believe that that's graphene because of the geometry. So we're going to confirm that afterwards. After we've confirmed this, we move on to transfer the graphene to the TEM grids. So basically what you would do is you would take a drop of isopropyl alcohol and you would use that to adhere these TEM grids, which I'm not sure you can see, but basically you'd adhere it to the copper, which has the graphene on it. And here's the blow up of what a TEM grid would look like. It has these gold grids, and then it also has this mesh of holy carbon underneath it to support whatever nanoparticle you want to attach. So the next step would be to etch away the copper. So basically, the diagram I just showed you is basically this. So it's a cartoon version of it. So you have copper, and then you have your graphene monolayer on top, and you also have your TEM grid, which has been adhered. So we want to etch it away. An analogy would be basically using a chisel to etch away or chisel away wood. So, and you can use lasers or you can use chemicals. In our case, we use chemicals to get rid of the copper, and leave just the graphene on the TEM grid. So our chemical we used was sodium persulfate, and it etches away the copper by a redox or reduction oxidation reaction. So your reactants are these. And then afterwards you get these edged products. So the sodium is a spectator ion, doesn't really do anything. But the persulfates break into sulfates, which stay in solution. And the copper gets attached to a sulfate, and that takes away the copper. So you're left with a TEM grid that has just the graphene. So the next step would be to characterize it using Raman spectroscopy. So Raman is essentially a technique where you transmit a laser through a sample in order to determine what you have. And it's based off vibrational energy and the composition of whatever you have. So on the left is the established signature for what graphene and other graphene-like substances have. It has the G peak, and it has a 2D peak. So when we Ramaned, we found this G peak, and we found this 2D peak. So it seems to suggest that we have multi-layer graphene. Now that we have the TEM grid with multi-layer graphene on it, we're going to create our graphene sandwiches. So essentially what you do is you just take two TEM grids and you just plop them together with some solvent inside. And in our case, we used 1,2-dichlorobenzene. Here's the structure. And we wanted to put it inside the solvent, inside the sandwich to create this. And here's an image of what it would ideally look like. As you can see, there's another grid underneath it. I'm not sure you can see it, but basically it's not entirely aligned. So now that we've created the sandwich, we're going to use EDS, or energy dispersive X-ray spectroscopy, to identify what we have. So the EDS is part of the SEM. So first we will take a look at our graphene sandwiches in the SEM to find a region of interest, which in this case would be this region, because all these strange looking things that look sort of like pockets of something. So the EDS uses X-rays and it sends it through, and it'll bump up the electrons in the atoms, and when the electrons fall back down, they'll also emit X-rays. And then depending on how they emit it, you can use it to figure out the chemical composition of whatever you're looking at. So in our case, we want to identify the solvent we had, which was dichlorobenzene. So we're looking for chlorine. And lo and behold, when we EDS this region, we found a chlorine spike. So this confirms that we have something that's chlorine-based inside. And since we didn't have anything apart from dichlorobenzene, which was chlorine-based, we have proven that we have a graphene sandwich with a solvent here. So in our experiment, we managed to create a dichlorobenzene graphene sandwich. This proves that you could put solvents inside a graphene sandwich. And another solvent you could use would be something like dimethyl sulfoxide. And this would allow you to sandwich biological molecules inside, such as like DNA. And once you've sandwiched a biomolecule inside, you could image it through transmission electron microscopy to see what it looks like. Now, one of the issues you might raise is that the atomic mass between DNA or another biomolecule and a solvent isn't so great, so you can't really see it. But you can remedy this using negative stains or positive stains. These stains essentially change the atomic mass of whatever sample you're looking at. So it can either stain the background, or you can either stain your sample, and this will create better contrast so you can actually image it. So keeping this in mind, and using the research that we did, you could very potentially research biomolecules and actually directly image them. And this is very powerful. Let me just give you an idea. Watson and Crick didn't really know the structure of DNA. They had to use a lot of indirect evidence. But if you had this technique, they could just put it inside the graphene sandwich, image it with a TEM, and they'd be able to pretty quickly figure out it's the double helix. So think about that. I mean, you could actually image what the biomolecule looks like, and that's big. And I'd like to acknowledge my mentor, Ashley Gibb, and also the principal investigator of our group, who's Alex Settle. Here's a picture of him. He really likes the Monticron. And I'd also like to thank the BNI SHARP program, which has provided me with this opportunity to do research with Zettel Group. Okay, thank you. Any questions?
Is part of how this works because does the graphene stick better to your solvent sandwich material than it does to the TEM grid? And is there any limitation that it won't stick to something?
So yeah, there is. So the carbon actually has van der Waals interactions with your solvent, so it'll actually stick to it and create a sandwich. So that's part of the reason why it works.
In your pack with the Raman, can you explain what's on the X and Y axes?
Sure.
And what are the G and 2D?
Okay. So Raman is more of a fingerprinting technique where you basically look at it and you just compare it to see if you have what you say you have. And on the y-axis you have the intensity, so that's basically how much laser light is scattered. And this is basically an arbitrary unit, so these are arbitrary numbers. But anyways, on the x-axis you have the Raman shift, which basically has to do with the laser wavelengths, or that's being sent. And when you compare these two, you notice that it looks very similar to the graphite, which is basically multi-layer graphene. And this allows you to identify it as graphene.
So I had a follow-up question to that.
Sure.
So the plot on the right, is there a way to tell how many layers of graphene you have just from the Raman spectrum?
So it actually has a lot to do with what it looks like. So you see this on the bottom right here? This is graphene. It's literally single layer graphene. This, and then on top of it is graphite, which is multi-layer graphene. So if it's multi-layer graphene, it'll actually have a different signature than single layer graphene. So since this resembles the graphite, which is multi-layer, it leads me to believe that we grew multi-layer graphene.
Right, but like, do the peaks sort of move around depending if you have like, say you have 3 layers of graphene, right? That's graphite.
Right.
Does that differ from what the peaks look like if you have 5 layers, 7 layers, 10 layers?
So you'll still have, typically the G peak will be higher than the 2D peak, so that's one of the identifying characteristics. And then in addition to that, but apart from that, basically you just look at the G peak. Is it higher than the 2D peak? If it is, it's typically multi-layer, but as you get higher and higher,
Mhm.
it'll just be more of a return.
Okay.
So it's sort of arbitrary, but it confirms that it's multi-layer.
I have a question.
Sure.
So on your EDS results, you showed chlorine as one of your peaks.
Sure.
Did you do any measurements on that sample in an area that you knew was not a sandwich to make sure you did not get a chlorine peak?
As a fact, I have some supplemental slides for that. Let me skip through these Raman ones. Whoops. Let me move to that. But yeah, we did have a control to test that. So you see this image? This is an EDS taken from just the sample holder itself, so it doesn't have anything on it. And we have a lot of aluminum, so that's to be expected because it's from the sample holder. And then we have a bit of carbon, but that's just background. Now, this chlorine peak, it's not really a peak. You can't really identify it, so there isn't chlorine. Now, when we did it earlier, we had more of a chlorine peak, so it was much higher, and because of that, we can confirm that there was chlorine in that sandwich-looking region. See, with this one, after the carbon, there's a dip, and then there's a much higher peak here, so you can confirm that that is chlorine. Whereas the other one, which was just the control, it was basically leveled off around here, and you couldn't distinctly tell that that was a peak. So that's why we can prove that that was chlorine indeed.
I'm sure it's really hard to create a monolayer for the graphite. How many layers would make it detrimental for you to do TEM?
So,
Like if you weren't able to create a monolayer, if
So-
you had a couple layers, would it
so
still work?
so for example, remember earlier how I was talking about the silicon-based systems and how they were like 50 nanometers thick?
Yeah.
Well, the reason why graphene is good is because it's angstroms thick, so I would think that as long as it's just a few layers, not like 50 layers, it'd be fine. So maybe like 2 layers, 3 layers, it'd be
Okay.
fine. But I'm not entirely sure about that.